Hi, in this series I've been investigating what it took to create an arcade-style shoot-'em-up on the Sinclair ZX Spectrum back in the 1980s. In the first episode, I introduced a high-level game design that I'll be using in this series. And in the second and most recent episode, I introduced our fictional programmer hero, Jack, as he attempted to create the game using ZX Basic. And he very quickly discovered that it just was not up to the task. And he learned that if he wanted to create a slick and playable game, he'd have to use something called machine code. But what exactly is machine code? Here in the mid-2020s, thanks to the emergence of AI agents like ChatGPT, Gemini and Copilot, we've become used to giving computers instructions in a natural language. But the Z80A at the heart of the ZX Spectrum is not capable of understanding instructions given in English. So what does it understand? The short answer to that is numbers, and those numbers are represented by electrical charges. But this also needs some qualification. The number system used by human beings is base 10, otherwise known as denary or more commonly decimal. Probably because most people have 10 fingers, we developed a number system with 10 symbols. Microprocessors like the Z80 use something called logic gates, which are built with transistors. And those transistors can be in one of two states, a low state or a high state, effectively off or on. This means that the natural number system for the Z80 is base 2, more commonly known as binary, which has two number symbols, 0 and 1. So when the Z80 is counting up, it starts with a 0 in the units place, as we would do, then it counts up to 1. But whereas we would continue with 2, 3, 4 and so on, the Z80 is now out of digits, so it must make a new number place. Now when we do this, because we're using base 10, each new number place is the next power of 10. Because the Z80 is working in base 2, each subsequent number place is a power of 2. So the first number place is of course units or ones, and for the second number place we multiply 1 by 2 to get 2's. So the Z80 can now continue counting by setting the 2's place to 1 and setting the 1's place back to 0. Then counting continues to 1, 1, and now we have to add another place, which will be 2 multiplied by 2, giving us 4. Now we go to 1, 0, 0, then 1, 0, 1, and so on. Just as each of our number places is a decimal digit, each of the number places on the Z80 is a binary digit, more commonly shortened to bit. Now the Z80 is an 8-bit microprocessor. What does that mean? Well, inside the Z80 are structures called registers that are used to temporarily store data while the Z80 is executing code. The largest number that each of these registers can store has 8 binary digits. We can work out the decimal equivalent of this by multiplying the place value for each digit. And if we add all those together, we get 255. So each register in an 8-bit microprocessor like the Z80 can store numbers from 0 to 255. You may have heard this size of binary number referred to as a byte. So given that the microprocessor understands only numbers, then it makes sense to use numbers to represent different instructions that the Z80 can obey. And that's exactly how machine code works. So where do these instructions come from? They come from external memory. In this case, memory chips in the ZX Spectrum, of which there are two types, read-only memory, ROM, or random access memory, RAM, which can be written as well as read. The Z80 is capable of requesting 1 byte at a time from this memory. Each byte is then transferred to the Z80 via 8 wires known as a data bus. Let's say we want to add two numbers together. For example, 2 plus 3. The Z80 has a special register labelled A, which is something called an accumulator. It's a register that can be used to perform arithmetic operations. Now, the instruction to store a number in A is 00111110. When the Z80 receives this instruction, it knows that the next thing it should expect is the number for it to store. So the next item on the data bus will be the number 2, which in binary is 00000010. The instruction for the Z80 to add a number to the number already in register A, the accumulator, is 11000110. Again, when the Z80 receives this instruction, it knows that the next thing it will receive is the number to add. In this case, that's 3, which is 00000011 in binary. Once this is received, the Z80 will perform the addition, leaving the result in the accumulator A. So 2 plus 3 is of course 5, and in binary that is 00000101. Now at this point you might be wondering how anybody manages to program in machine code if they have to remember all those long binary numbers. Well, one thing we could do of course is convert them to decimal, and in this case our sequence would look like this. But because 10 is not a power of 2, decimal is not a particularly useful base for us to convert binary to. Ideally, we want to choose a number base that is a power of 2. In the past, base 8, otherwise known as octal, was often used. But by the 1980s, it was more common to use base 16, more commonly known as hexadecimal. Wait a minute, you might be saying. How can you have a number base higher than 10? There aren't enough digits. What do you do after 9? Well, mathematicians came up with a clever idea of using letters of the alphabet to make up the extra symbols. So in hexadecimal, for the 6 digits that come after 9, we'd simply use the letters A to F. Now, a single hexadecimal digit can store values that would occupy 4 binary digits, sometimes referred to as a nibble. So therefore, to represent an 8-bit binary number, we need just 2 hexadecimal digits. Using hexadecimal, our machine code sequence looks like this. Note that it's usual when using hexadecimal in computing, as with binary, to include any leading zeros. So that's a lot neater than using decimal. But even so, is someone really expected to memorize a load of hexadecimal numbers? Well, no. Realizing the impracticality of this, the designers of microprocessors like the Z80 generated a set of mnemonics for each instruction to make them easier to remember. If we were to use the mnemonics for our short routine with the equivalent hex codes next to them, it would look like this. Now add is fairly self-explanatory. LD may be less so until you understand that it's short for load. In other words, this instruction is saying load the number 2 into the accumulator A. These mnemonics collectively are known as an assembly language. But beware, the Z80 doesn't understand assembly language any more than it understands the English language, or ZX Basic for that matter. So while assembly language is a convenient way to write code such that it's readable and more easily understood by a human being, it does still need to be converted to the equivalent machine code before the Z80 can make use of it. Okay, let's assume Jack has done a bit of research and now understands, at least at a high level, what machine code is. At this point, he might very well be hunting through the ZX Spectrum manual to find out how he switches it from ZX Basic programming mode to machine code programming mode. But he's going to be sorely disappointed. The ZX Spectrum does have support for running user-created machine code programs, but that support is minimal and it requires a bit of extra effort on the half of the programmer. So how does Jack get a machine code program into the ZX Spectrum? Well, to answer this, let's take a closer look at how the Z80 gets those instructions from memory. To do this, it needs to let the memory chips know which memory location it wants data from. And it does this by putting a number onto another bus called the address bus, which once again is a set of wires connecting the Z80 to the memory chips. Now, if the address bus was also 8 bits, that would mean we could only have 256 memory locations. The first one is numbered 0. This is really not enough room to do anything of much use. So instead, the Z80 has a 16-bit address bus. If we use the same method we used before of adding up the first 16 powers of 2, we'll see that the largest memory location that can be addressed is 65535. So, given that we start numbering memory locations at 0, we can address 65,536 bytes. Now, throwing such large numbers around is a bit unwieldy, so it's usual to follow the convention that 1024 bytes is referred to as a kilobyte, or 1K, and 64 of these amount to 65,536 bytes. So our maximum addressable memory is 64K. Now the Z80 maintains a 16-bit number called a program counter, usually abbreviated to PC. This points to the address of the next instruction or data item the Z80 will retrieve. So when it's ready for that instruction or data, it puts the number in the PC onto the address bus, and the memory chips use that to fetch the correct byte and put it onto the data bus. Once the Z80 has retrieved the data, it then increments the program counter, which is a fancy way of saying it adds 1 to the number stored there, so that it's ready to retrieve the next instruction or data item. So where in this 64K of memory should Jack put his machine code program? Well, let's have a look at how this memory is used by the ZX Spectrum with a diagram commonly known as a memory map. The first 16K of memory is allocated to the ROM, which contains the ZX Spectrum operating system and ZX Basic interpreter. So that runs from address 0 to 16383. As you can see, these numbers seem a bit random in decimal, but if we use hexadecimal, that address range is 0000 to 3FFF, which is a lot neater. From now on, I'm going to use the prefix 0x to indicate a hexadecimal number. So if we take 16K away from 64K, we're left with 48K for RAM, which is where the 48K in the computer's name comes from. However, not all of that 48K is available for us to use. The first 6,912 bytes is where the contents of the screen are stored, and we'll be taking a closer look at that in the next episode. Then there are 256 bytes, which are used as a printer buffer if you're using the ZX printer. This is followed by 182 bytes of system variables. These system variables are various bits of data that the operating system uses to keep track of operations. We'll be taking a closer look at one of these shortly. From 23734, that's hex 5C-B6 upwards, things are a little less rigid and will start to change depending on what we're currently doing with the machine and how big our basic program is. But in this space, we'll potentially find some areas reserved for microdrives and input-output devices, any basic program that's currently in the machine, any variables created while the basic program is running, any basic command that's being entered or a copy of any basic program line that's currently being edited, any data being used for input in a basic program, and then a whole bunch of temporary structures which get larger or smaller as a basic program is running. These include, for example, the go sub stack, which BASIC uses to remember where to return to when it encounters a return statement after a go sub command. Finally, at the very top of RAM is an area where user-defined graphics are stored. So with all that going on, where is it safe to put machine code? Well, the way that user-defined graphics, or UDGs, work gives us a clue. If you watched the previous episode, you'll know that using UDGs was something that Jack tried when he was trying to draw sprites in BASIC. When you define UDGs, the patterns that you set will remain intact, even if you enter a new command to clear the spectrum's memory. However, they will be lost if you disconnect the power to the machine. So this means UDGs are stored in RAM, but somehow they're protected from being cleared out along with everything else when the new command is executed. What gives them that protection is a system variable called ramtop. This sets the last byte that can be used by the BASIC system, which is also the last byte that new will clear. We can set this system variable to a new value using the clear command. So, for example, if we wanted to reserve the topmost 16K of RAM, we could issue the command clear 49151. This will protect the area of RAM from 49152, which is C000 in hex, to 65535, which is FFFF in hex. So you can be sure that anything in that range will not be overwritten by the BASIC system or cleared by the new command. Of course, once you power down the spectrum, then the contents of that part of RAM will be lost along with everything else. And on rebooting the system, ramtop will have been reset to its default value. Okay, so now Jack has set aside some safe space for his machine code program. But how does he get it into that memory? Well, the easiest way is to use another command he was introduced to when setting up user-defined graphics, poke. Poke is used to put data directly into a specific memory location, and it takes the form poke a, n, where a is an address and n is the value to put there. Now, of course, this command takes decimal values, so Jack writes a simple program to enable him to enter program data as hexadecimal values. So now he can use this to enter the simple machine code program we looked at earlier to add two numbers together. Okay, but once the program is in memory, how does Jack run it? Again, looking back at the program to define user-defined graphics gives him a clue. This introduced the USR function, which Jack used to obtain the address in memory of the start of the UDG characters. When used in this context, it converts the character to an address, which was then used by the poke command. However, USR can be used in another context. If it's given an address as an argument rather than a character, it will attempt to call a machine code routine at that address. USR is not a standalone command though, it's a function that needs to be called from within another command, and it will return a value to that command. One common way of doing this is to use it with the print command like this, print USR 49152. But when Jack tries to execute this, this is what happens. His ZX Spectrum crashes. Why was this? Well, within a BASIC program, even if Jack doesn't enter an explicit stop command, if the last line of the program is reached, then execution ends. This isn't the case with a machine code program because the Z80 has no way of knowing where your program ends. And so after it executed the add A3 instruction, it merrily carried on fetching instructions from memory until it either encountered random instructions that caused it to upset the operating system state, leading to a crash, or until it wrapped around to address 0, which is the start of the ROM, which will also have the effect of restarting the machine. The Z80 doesn't have the equivalent of BASIC's stop instruction. However, note that I said USR attempts to call a machine code routine. It uses the call instruction, which is the Z80's equivalent of BASIC's GoSub. And just like with GoSub, we can use a return instruction, which is ret in assembly language, to return to the calling routine. So Jack's revised program looks like this. So Jack updates his data, gets the program into memory and tries again. This time, instead of a crash, he gets a value printed out. But hang on, that's not the expected result of 5. What's going on here? Does he have a faulty Z80 that isn't adding properly? No. I did say that USR is a function that returns a result. But where does it get that result from? Well, unfortunately for Jack, it's not the A register, the accumulator. Let's have a look at some of the other 8-bit registers in the Z80. Here they are: A, F, B, C, D, E, H, L. Don't worry for now about that rather odd sequence of letters. I'll be coming back to this in a later episode. While each of these registers can be used independently to store an 8-bit value, the Z80 also has a clever feature where some of them can be paired together to hold a 16-bit value. So you could store 16-bit values in BC, DE and HL, where BD and H store the most significant 8 bits and C, E and L store the least significant 8 bits. It's the 16-bit value in BC that's returned by USR. So if Jack wants the result of his calculation to be printed correctly, he's going to have to transfer it into BC first. Well, okay, but how do we transfer an 8-bit value into a 16-bit register? The answer is that we divide and conquer, and we set each 8-bit register individually. Now, because we're passing back an 8-bit value, B is always going to be 0. So we can just set it to 0 using a load command with a direct argument of 0. Now we can simply copy the contents of the A register into C. We use another form of the load command for this: load C, A. And here's the revised program. Now, when Jack reruns his program, he sees the correct result, 5. So now Jack knows how to get a machine code program into the Spectrum and how to run it. Next, he wants to repeat his sprite display experiments from BASIC, but this time using the power of machine code. And to do that, he'll have to dive into the inner workings of the ZX Spectrum display. And that's a topic that we'll pick up in the next episode. See you there.